may often hear that the quantum mechanical description of a particle is referred with the term state instead of wave function. What is state? Well, this is one more abstraction we can use to make the picture of the world look a little bit simpler for us. As we remember, wave functions form a linear vector space. The vectors in that space are square integrable functions. But there is a wonderful property of linear vector spaces for which everybody loves them. It does not matter what kind of object represent the vectors in the vector space. Linear vector space is an abstraction which allows us to forget about the physical and mathematical nature of the vectors. As soon as we know that some objects form a vector space, we can use with them all the instruments that linear algebra gives us for this. And the first thing we are going to do is to employ the notation used very often in linear algebra. Consider again that we have the wave function of whatever decomposition in some basis. For the sake of clarity, let's at first consider the finite-dimensional space of dimensionality n big. Its basis consists of n big vectors, and the sum of wave function decomposition in this basis has n elements. Each element of this sum is a basis vector multiplied by a coefficient, which we call its amplitude. Okay, now let's consider a special space, which consists of columns of n digits. We will call them vector columns. Each element of our basis E, we will match a column consisting of all zeros except one place where we put 1. The first vector of our basis, E1, will correspond to the column where 1 resides on the first place, and other elements of the column are zeros. The second vector, E2, corresponds to the column with 1 residing on the second place, and all other elements are zeros, etc. Since I told you that this set of columns is a vector space, we remember that we have to define two operations with them. First, multiplication of a vector by a scalar, which we will define as multiplication of all column elements by the scalar. And second, the sum of two vectors, which we define as a column, each element of which is the sum of corresponding elements of the columns we add up. Okay, the set of columns defined like this is indeed a linear vector space. And for each basis element E, we have a column, which represents this basis vector as a column vector. Having all this, we can now determine which column vector corresponds to our initial wave function through its decomposition in the basis E. First, we multiply each column vector by its amplitude from our decomposition, just because we can. This gives us columns with all zeros except one place, where the corresponding amplitude resides. And second, we add all these columns to obtain just one column, all consisting of our amplitudes. The thing we just have done, mathematicians call the isomorphism. For the vector space of wave functions, we built an isomorphic vector space consisting of vector columns. And in this isomorphic space, our wave function is represented by the column consisting of amplitudes of this wave function decomposition in some basis of our choice. Now the space we just built, we will call the state space of the system. And its elements, columns, we will call states. It is often more convenient to us to work with the state space representation of the system than with wave functions. First of all, we have a very convenient notation for it, called Dirac's notation, after its author Paul Dirac. We are going to introduce and use this notation on week 4. And second, there are characteristics of a particle which we cannot describe in the terms of wave functions, but we can do it in the terms of the column vectors. What we just did for a finite dimensional space, we surely can do with infinite dimensional space. In this case, the columns we would have to introduce will have the beginning or the first element, but no end or the last element. These are going to be endless columns. In some sense, it can be done even with a continuous basis, like that of delta functions. But we are not going to concentrate on that. We are much more interested in the case of finite numbers of dimensions. Let's see why.